Hello, so today we're going to talk about the basic differentiation rules, basic derivatives, and then also how that applies to different concepts of rates of change. So what we did last time with the whole tangent, with the limits problem, we're not going to do that ever again. We're going to talk about how the different rules work. So first off, the derivative of a constant function is simply 0. So if I just have f of x equals 5, or negative 2, or 20, or just some constant number, no variable in the slightest, the derivative of that is given as 0. Very straightforward. It has to go away. There has to be a variable for the derivative to exist. Again, this can go back to the tangent line problem, where if you would do f of x plus delta x, there is no x plug in, so it would still be 5. They would cancel out, leaving 0 over delta x with just 0. So, works out kind of nice. Now, the power rule. This is your most basic and fundamental derivative. From here, everything else is pretty much based off of, except for different trig problems and other things. So if you have your function f of x equals x to the n power, where n is just some rational number, positive, negative, fractions, doesn't matter, it's a number. The derivative is the following. The derivative becomes the exponent now goes in front of the function times the function times x now raised to a lower power. So for example, if f of x was x to the 5th power, the 5 goes in front, the exponent now goes in front, and we decrease the new exponent by 1. That's why it's 5x to the 4th. Had this been x to the 7th, the derivative, we would bring the 7 in front and decrease the exponent by 1. So it would be 7x to the 6th. So let's use this concept. So f of x equals x squared plus 5 minus 3x to the negative 2nd. So the derivative, again, we take the exponent, move it in front. So 2 goes there. When I decrease 2 by 1, I just get 1. So I get 2x. 5 is a constant, so it goes away. I move the negative 2 in front. Since there's already negative 3 there, they multiply. Negative 3 times negative 2 is a positive 6. And again, I decrease the exponent by 1. If you like to go one step further and rewrite it so there's a positive exponent, this becomes 2x plus 6 over x cubed. Either way is perfectly fine. There's no necessarily reason to one way to write it correctly or not. So that's it. You take the exponent, move it in front, and decrease the exponent by 1. Had there been a number already in front of it, you multiply those two numbers together to get a new number. And again, you still decrease the exponent by 1. If there is no variable, it goes away. So we have f of x equals x to the 5th minus 4 over x to the 4th. So before I do everything, you always want to try and write things in exponential form. So the x to the 5th is fine, but I should rewrite this as minus 4x to the negative 4th. That way I can apply my simple power rule. So our derivative, we again move the 5 in front, decrease the exponent by 1, so it's 5x to the 4th. We move the exponent in front, since it's already there, they multiply. Negative 4 times negative 4, positive 16. Decrease the exponent by 1. And again, if you would like to write it so it has a positive exponent, this becomes 16 over x to the 5th. Pretty straightforward. Now, in this particular case, we are going to talk about how to take derivatives when they are quotients, when we're dividing a function by a function. But if your denominator is ever a single term, a monomial, you always want to divide that term into each piece up top. You do not want to think of this as a quotient rule, which we will discuss later. So I'm going to divide x squared into each piece and go x cubed divided by x squared is just x. X squareds will cancel. This becomes 4 over x squared, so 4x to the negative 2nd. This allows us to take the derivative much, much easier. We could still use the quotient rule once we learn it, but why go through so much effort when it now is a very straightforward function? Again, for a derivative, the exponent comes in front. Since x is really x to the 1st, so 1 comes in front. And if I decrease the exponent by 1, it becomes x to the 0, which is just 1. So you'll notice, if you're taking the derivative and just simply x, or t, or q, or whatever the variable happens to be, the number in front of it is all that's left over. Because you bring a 1 in front, doesn't change anything, and the variable now goes away. Since it's a constant, there's no variable, the negative 3 derivative is 0. Here I bring the 2 in front, so 4 times negative 2 is a negative 8. Decrease the exponent by 1, it's x to the negative 3rd. So again, I could rewrite it as 1 minus 8 over x cubed. So again, the goal is whenever you have a quotient like this, you want to divide the denominator, if it's a monomial, into each piece up top. Had this been a binomial or trinomial, we would have to use our quotient rule, which will be discussed in a later video. Again, the whole key for all these problems is to rewrite them so they're in exponential form. So I don't want to leave square roots or cube roots or whatever roots the way they are. Remember, the square root is really the same thing as the 1/2 power. So this really is x to the 1/2. This right here is really x to the 1/3, so minus 6x to the 1/3 power. Now that I have this, I can now go ahead and take my actual derivative. Again, the exponent goes in front, and I decrease the exponent by 1. So 1/2 minus 1 is negative 1/2. I bring the exponent in front, 6 times 1/3 is 2. If I decrease it by 1, it's negative 2/3. And again, technically I could rewrite this so they're positive exponents. So it becomes 1 over 2x to the 1/2 minus 2 over x to the 2/3. The reason why this 2 is on the bottom, because it's 1/2. It's already on the bottom. Whereas this 2 is up top, that's why it stays up top. Technically, for some of these problems, we should maybe go a little bit further, because technically we have a square root in the denominator, we can't have that. We have a cube root in the denominator, technically can't have it, stuff like that. We're not going to get into that kind of simplification. You're now reaching the point where you're doing algebra manipulation. For the most part, unless they state otherwise on the AP test, they want you to do the calculus part correctly and do a basic transfer from there. I mean, technically, this whole x and negative 1/2 part is fine. That might even appear as an answer. They're not really worried about your algebra manipulation skills. They're more worried about, can you understand the calculus behind what's going on. So it's ultimately up to you. At least in my class, I'm perfectly happy with this answer right here. I'm also okay with this answer right here. There is no need to take this any further. If this was a multiple choice question and neither one of those appeared, then maybe they want you to go a little bit further than that. It's all depending upon the question itself. So we also have some basic trig functions to talk about. If we're talking about f of x equals sine of x, its derivative is cosine. Whereas if the function is cosine, its derivative is negative sine. Sine becomes cosine, cosine becomes negative sine. How you remember that, you need to be careful. If you switch that up, it screws up every single sine and cosine problem. I can speak from experience on that when I was in high school and did that mistake. So if I want to find the derivative of f of x equals 2 sine of x, well, the 2 stays where it is. Derivative of sine is cosine, becomes 2 cosine of x. Pretty easy. All we had to really worry about was the sine, it became cosine. Here, for this function, f of x equals x plus 5 cosine x. So its derivative, well, derivative of x is just simply 1. Derivative of 5 cosine x is negative 5 sine x. Because cosine is negative sine, so negative times 5 is a negative 5. That's why it's negative 5 sine x. So those trig functions are very straightforward, very easy. There are other trig functions we'll talk about in a later date for their derivatives. The tangent, secant, cosecant, cotangent, all of them. Now, one practical application for calculus is in the application of physics, where one thing that you'll see in physics is a position of a free-falling object, where we neglect air resistance. Because technically there is air resistance as you're falling, it's not just, you just fall, no big deal. This is the equation, though, for the general equation for this. S of t, where s is the position function, equals 1/2 gt squared plus v sub 0 t plus f sub 0. G is your gravity, acceleration due to gravity. T is time, obviously. V0 is your initial velocity, and S0 is your initial position. So given a word problem, you can plug in all the information to this, initial velocity, initial position, maybe the actual position at the end, something like that, to figure out how to solve this kind of problem. Now, G depends upon what kind of unit you're working with. G will either be negative 32 feet per second squared if you're working in standard units, or negative 9.8 meters per second squared if you're working in metric units. Now, both those are actual approximations. I believe acceleration for metric is really negative 9.801 or something like that. And I think for standard it's like negative 32.124 or something along those lines. It's been a while since I've dealt with physics, so I'm not 100% sure about that. Either way, though, for this particular For the most part, you're going to use approximations for this. If your teacher wants you to use the more exact values, verify what they are either with your teacher or online. Now, velocity is pretty easy for finding for a free-falling object, because velocity is the derivative of position. So if I have my position function, I take my derivative, I now have the velocity function. And we'll talk about acceleration as well in a later date. So, at time t equals 0, a diver jumps from a platform diving board that is 32 feet above the water. So that's our initial, because time is 0. So our initial position is 32 feet. Diver has an initial velocity, v sub 0, of 16 feet per second. When does the diver hit the water? What is the diver's velocity at impact? So again, if you remember from your s of t function, I need 1/2 gt squared plus v sub 0 t plus s of 0. So I need g. Well, if I'm in standard units, g is going to be our negative 32 feet per second squared. So I have 1/2 negative 32 t squared plus v sub 0 t plus s of 0. So the position function works out to be negative 16t squared plus 16t plus 32. We have to work with the actual position function in order to solve the problem. Without that, nothing else makes sense. And again, all the information came from the word problem itself, the initial position, 32 feet, initial velocity, and we know g is negative 32 because we're working in standard units. Had this been metric units, g would have been negative 9.8. Now, when does the diver hit the water? Well, when you think about it, what is the height of the water? Water is at a height of 0 because we're 32 feet above the water. So I want to know, when does this function equal 0? So this is a quadratic, so I need to solve this using our quadratic methods. Now, first thing you want to do for any sort of function you're trying to solve, if you can cancel numbers out that they all have in common, you make your life so much easier. Notice, negative 16, positive 32. They all have a 16 in common. So I'm going to divide everything by negative 16. Now we have no numbers in front of our t squared. I just have simply t squared minus t minus 2 equals 0. This is now a much simpler problem to solve, because now I can factor this much easier. I have t minus 2 and t plus 1. T equals 2 and negative 1. Now, negative 1 makes no sense. I can't have a possibility of a negative 1 second. That means I go back in time 1 second. And no, illogical. So, when does the diver hit the water? After 2 seconds. It takes them 2 seconds to hit the water. The next part, what is the diver's velocity at impact? Well, I want to know what is the velocity when t equals 2. So I need to find the velocity function. Again, velocity is derivative of position. So I take my derivative of the position function, the negative 16t squared plus 16t plus 32. I get negative 32t plus 16. So I plug in 2 to this. Negative 32 times 2 plus 16. We get negative... Whoa, that wasn't supposed to happen. Okay. Sorry about that. We get negative 64 plus 16, which is a negative 48. So our velocity, and I'll write it over here because I need a little more room. Our velocity at 2 is negative 48 feet per second. Now remember, velocity is simply talking about direction. Speed is always the absolute value. So if they ask for the speed at impact, we would just say 48 feet per second. But velocity being negative tells us our velocity is going down, or going down. If velocity had been positive, it would imply we're going up, which makes, again, no sense. We can't dive upwards. We're not a rocket ship. So that's how you solve a basic free-falling problem using your position function. You identify initial position, initial velocity from the word problem itself. Both those could be 0. If you're talking about it's from ground level, position is 0. If you are just simply like, if you just fall off a cliff or you just like drop something off a building, the initial velocity is 0 because nothing was, it was just in your hand or you were just standing there. So use the word problem itself to figure out that information. Gravity you know based off what units you are, and then go from there. Okay? So that's your basics of derivatives. It gets a little more complex from here, but we'll talk about the different types of rules for how to use these derivatives. Because they're not all just simply basic functions. They get more complex. So I will see you next time.